Hello and welcome to screencast number 7. My apologies for number 6. I didn't realize I had run over time, and I was trying to explain this picture when I ran out of time, so we're going to pick up from here. So we are Chapter 20, Conventional Energy Alternatives, and what you are looking at are hybrid poplar trees that have been specially bred for fast growth in dense plantation, and they are harvested for biopower. It is considered a renewable energy, but it has some environmental impacts. These monoculture plantations may replace natural systems over large areas, and they do not function ecologically as forests. You might get some squirrels and you might get some birds, but they're not going to be forests because they're going to be cut down and harvested and then replanted again. But poplars, as I said, they do grow very, very fast, and they're tall and thin. Okay, so now we're going to look at different combustion strategies, and there's varying scales of production, again, depending on the substance that you are going to use. We can burn this biomass and this bioenergy just like we do with our coal fire plants that we've talked about in the past. They're going to combust, that means that they're going to heat water. They're going to create steam. That steam is going to be used to turn turbines and generators, and they're able to then generate electricity, just like we saw with our coal fire plants. But much of the biopower that is produced from the power plants that we could use for it is used in what we call cogeneration. And that means that it's being used along with coal. It's not just being used by itself. So in coal-fired plants, they will use wood chips and wood pellets and other biomass, and they will introduce with the coal into a really high efficiency type of boiler, and this is referred to as co-firing. And it can substitute biomass for up to 15% of the coal with only minor equipment modifications, and there's no appreciable loss of any sort of efficiency if you use it. So co-firing is relatively easy and inexpensive way for the utilities to expand their use of renewable energy. And as you can imagine, it's going to cut down on the amount of carbon dioxide that is released, as well as it's going to cut down on the amount of coal needed, and that whole chain reaction events that we have already talked about. We can also harness power through a process called gasification, and we had mentioned this before somewhere around page 537, because I'm reading that right from your book, so I know that. The biomass is vaporized at an extremely high temperature in the absence of oxygen, and with this it can generate methanol. And we know that methanol is an energy gas that could be used. This creates a gaseous mixture that will also include hydrogen, carbon monoxide, carbon dioxide, and methane. And we can use those to generate electricity when they're used to turn a gas turbine and propel the generator in the power plant. We treat the gas from gasification in various ways to be able to produce the methanol, which is a type of synthetic diesel fuel, and we isolate that hydrogen for use in hydrogen fuel cells that we've heard a mention of. So this is an alternative method of heating biomass in the absence of oxygen, and you might have heard this before. We do this in the process of pyrolysis, and that's how we produce that liquid fuel. That liquid fuel we're going to call pyrolysis oil, and then this can be burned to generate electricity. Let's talk about these combustion strategies and look at them in terms of scales of production. So on small scales, farmers, ranchers, and villagers, they can operate modular bi-power systems that use livestock manure to generate electricity. Even small household biodigesters can provide a portable and decentralized energy production for remote rural areas where, believe it or not, electricity doesn't exist. On the larger scale, when we talk about industries, we can see as forest products, industries are using their waste to generate power, and industrialized farmers, the big farmers, are growing bioenergy crops. We can go back and we can look at Sweden, since Sweden is using most, has all of those trees and using that as part of their biomass. What they are doing is right now, the biomass that provides more fuel for electricity generation than coal and oil or natural gas comes from pulp mill liquors. And pulp mill liquors are just after you have this residual like chips, and they get into water and they actually begin to ferment in the water because there's naturally occurring yeast there. So they use these as a main source of energy. They also use some of the solid wood waste, and they use municipal solid waste. And what this has done is 1/5 of their nation's energy supply comes from this biomass. They also use biogas from digestion as well. The United States does have several dozen biomass-fueled power plants that exist and are operating, and a lot of their coal-firing plants are experimenting with co-firing. So we're seeing that happen. As you can imagine, there's going to be some drawbacks and some benefits from this as well. And what we're seeing is that we are enhancing energy efficiency. This is the benefits because we're recycling waste products. The biopower is helping to move our utilities and our industries in a sustainable direction, so that's a plus. The U.S. forest products industry now obtains over half of its energy by combusting the waste it recycles, including the woody waste and again the liquor from the pulp mill processing. Biopower also helps mitigate climate change because it reduces the carbon dioxide emissions. It captures the landfill gases like methane. That is a major proponent to greenhouse gases. And it benefits human health because you're not exposed to those toxins. By replacing coal and coal firing and combustion areas, the biopower reduces emissions of sulfur dioxide because plant matter, unlike coal, contains no appreciable sulfur content. The biomass resources tend to be geographically widespread, well dispersed, and when they use them, they can actually help rural economies and reduce many of the nation's dependencies on imported fuels. Those are the benefits. Okay, there are disadvantages, there are drawbacks. And one of the things is when we use that biomass power, we're burning the crops, we're burning the plant matter for the power, and what we're doing is we're depriving the soil of the nutrients it would have gained from the plant matter's decomposition. You know, we saw in our agriculture chapter that they weren't fully tilling the land, that they were leaving crops so that they could die and be decomposed and add nutrients to the soil. So we're not allowing this to happen, and essentially we're drawing fertility from the soil and we're never returning it. So the soil becomes progressively depleted. So that's a huge drawback because we know what happens when it gets too depleted. When we burn crops or plant matter as fuel that we're going to see coming up, that also is going to deprive the soil. The depletion of soil fertility is a major long-term problem that we have to focus on. It's one reason that relying solely on bioenergy is not a sustainable option. It can be used in conjunction, but we've got to have a way of putting the nutrition back into the soil. All right, so the last thing that we're going to look at is ethanol being used to power automobiles. And liquid fuels from biomass sources are powering millions of vehicles on today's roads. There's two primary biofuels that have been developed so far, and that's ethanol that we use for gasoline engines and biodiesel that we use for diesel engines. So the way that ethanol is made is by the same way that we make beer or wine, and it's a fermenting process that our carbohydrate-rich crops like corn will go through. The process is similar to brewing beer, where the fermentation and the carbohydrates are converted to sugars and then to ethanol. In 1990, the Clean Air Act amendment and generous government subsidies allowed ethanol to widely be added to gasoline in the United States to reduce automotive emissions. In 2012, the United States produced more than 13.3 billion gallons of ethanol, mostly from corn, as I had stated before, and more than 200 U.S. ethanol production facilities are operating at this time. The Energy Independence and Security Act that was passed by Congress in 2007 mandated production and use of 36 billion gallons of ethanol per year, and they wanted this in place by 2022. So our vehicles today have been made to be flexible fuel vehicles where they can run on gasoline that is blended up with about 10% ethanol. And more vehicles are being produced that can run primarily on ethanol. In Sweden, since we've used Sweden as examples throughout this chapter, Sweden has public buses that run on ethanol. The U.S. Big Three automakers are now producing the flexible fuel vehicles. They run on a mixture called E85 that has about 85% ethanol and only 15% gas. So there's about 9 million cars on the U.S. roads today that can run this way, but as you know, most gas stations do not yet offer E85. So drivers often fill these cars with the conventional gasoline, but this situation is changing as the infrastructure for ethanol increases. In Brazil, they use sugarcane residue. They crush the sugarcane and they make ethanol out of that, and that is referred to as bagasse. And I don't speak Portuguese, so I hope I pronounced that correctly. Half of all the new Brazilian cars are flexible fuel cars, and ethanol from sugarcane accounts for about 40% of all the automotive fuel that Brazil drivers uses. Okay, we're going to end this here, but we will continue talking about ethanol in our next screencast.